In this section, we're going to talk about what happens when we mix together aqueous solutions and some of the types of reactions that can occur. But before we do that, we need to review slash learn what happens to ionic compounds when you dissolve them in water. So if we take, for example, NaCl, solid, and we dissolve it in water, it will break up into Na plus aqueous plus Cl minus aqueous. So essentially what's happening is the sodium chloride disassociates into its ions in solution. And if you mix together multiple solutions, these ions can then interact with each other potentially. Before we talk about this though, I want to talk a little bit about what's actually going on here. And to do that, you're going to have to take my word for something. And that word is that essentially water is a polar molecule. So water, for whatever reason that we'll talk about later on in the course, has a partially negative oxygen and the hydrogens are partially positive. So this delta means partially. So this is partially minus and these are partially positive. So if we wanted to melt NaCl and separate the ions, we would have to add a tremendous amount of energy. But if we add water, it can stabilize these ions. So if we have Na plus, it would want to interact with the oxygens of water because the oxygens are partially negative and opposite charges attract. So this sodium becomes solvated, and there'd be one above and one below, and it may not necessarily be 6 molecules. This is not to scale, but basically the sodium plus becomes solvated. Similarly, the Cl minus will interact with the partially positive hydrogens of water because they are partially positively charged. And again, opposites attract. So what you have is this situation where some ionic compounds, and we'll talk about which ones in a couple of minutes, can break up into their ions in solution and become solvated, and the charges are stabilized by the polar water molecules. As you'll learn later on in this course, this is why salt will dissolve in water, but salt won't dissolve in a non-polar solvent, like for example, gasoline. So let's look at another example. If we have KNO3 solid potassium nitrate, notice that this contains polyatomic ion nitrate. This will break up into the ion K plus aqueous plus NO3 minus aqueous. So it breaks up into its ions. Or if we have calcium acetate, CH3, COO2, this breaks up in, this is acetate, this breaks up into Ca2 plus aqueous plus CH3COO minus aqueous, and because there's 2 here, we need to get 2 of those when they break up. So ionic compounds dissociate in water. In other textbooks, they talk about how ionic compounds are electrolytes. And if you've heard of Gatorade, which is full of electrolytes, well, Gatorade has ionic compounds. The primary one is sodium chloride, and then there's some potassium chloride in there as well, and probably some other things like magnesium and so on. But what that means is, the electrolytes, is that there are these charged ions in solution. And when you dissolve ionic compounds in water, because of this positive charge being attracted to the partially negative oxygen and the negative charge being attracted to the partially positive hydrogen, these ions dissociate in solution even at room temperature. So this is what happens in solution. Well, it turns out that if you mix multiple of these things, they can cross-interact. And here's an example of that. If we mix solutions that contain Pb2 plus and I minus, the Pb2 plus and the I minus interact with each other to form something that's not soluble in water. And what you see is this yellow precipitate. If you've heard of lead paint contains lead carbonate. Lead carbonate is a white color. All paints start off being white, and it used to be used as a pigment in paint until it was found that sometimes kids eat it, and it can be toxic for their brain development or their brain function. So they don't use it anymore because it's toxic. But that forms between lead 2 plus and CO3 2 minus. It forms an insoluble compound, lead carbonate. So these are just an example of these two things coming together and forming a solid. So you may ask yourself, well, why doesn't lead iodide dissolve in water? Technically, lead 2 iodide dissolve in water. Well, the reason for that is based on these solubility rules. Now, these solubility rules are empirical. So what that means is they are experiment based. And I have another copy of the solubility rules here, and then this will allow me to write some stuff down here, so I want to use them here. So these are empirical solubility rules. Scientists literally tried to dissolve stuff and saw if it would dissolve. And then based on that, they came up with this table of solubility rules. So first thing we have is your soluble cations. Remember, cations are positively charged ions. Those are your 1A metals and ammonium. And there are no exceptions. All 1A metal and ammonium compounds are soluble in water. Soluble anions, nitrate and acetate. There are no exceptions. Chloride, bromide, and iodide are usually soluble, but unless they're with lead, or excuse me, silver, mercury, or lead. And sulfate compounds are usually soluble unless they're with strontium, barium, mercury, and lead. I should note that solubility tables like this, which you do need to know, are somewhat different depending on where you look. And the reason for that is soluble is a qualitative term. So what one considers soluble, another may not. But these are the general rules you need to know for this course. Now let's look at insoluble compounds. So these are soluble compounds. Usually they're soluble. Again, there are a couple of exceptions, but usually they're soluble. For insoluble anions, you have carbonate, phosphate, sulfide, and hydroxide. And there are exceptions for carbonate and phosphate that aren't really exceptions, 1A metal and ammonia, because all 1A metal and ammonium salts are soluble. For sulfide and hydroxide, there are a couple of exceptions. You have the 1A metals and ammonium, but those aren't really exceptions because, again, they're always soluble. But calcium, strontium, and barium are somewhat soluble for these different compounds. So these are solubility rules, which again are empirical, which means they're evidence-based. Someone actually took whatever, ammonium chloride, and saw if it would dissolve. Or they took silver 1 chloride and found out that it wouldn't. And that's where these rules came from. So let's look at how one might apply these rules. Let's look at Na2CO3. And we want to decide if it's soluble or insoluble. Well, if you see a 1A metal, sodium, lithium, sodium, potassium, so on and so forth, if you see a 1A metal, it's always soluble. So this, that kind of looks like a minus, so I'm going to put it like this instead. This is soluble. Let's look at another example. Ca2, Ca3, PO4, 2, calcium phosphate. So if we look here, there's no solubility rule for calcium, right? These are your soluble cations. Calcium's a cation, it's 2 plus. Here we have phosphate, which does have a solubility rule. Insoluble anions. Phosphates are generally insoluble. So we can't use calcium to figure it out. We have to use phosphate. Well, is calcium an exception? It is not. So this is insoluble. Notice, again, we found phosphate on the list. It's under insoluble compounds, and calcium is not an exception. So that's how we're using the table. Let's look at copper 2 sulfate. For copper 2 sulfate, in this case, we first try to find copper, but you'll notice the only cations on the table are the 1A metals and ammonium. All the other cations, all the other species that are both soluble and insoluble are anions. So copper doesn't have a rule. Let's look for sulfate, the anion. Sulfate does have a rule. It's generally a soluble compound. Is copper an exception? It is not. So therefore, this is soluble. And then finally, let's look at AgCl. Again, the metal doesn't have a rule if it's not a 1A metal or ammonium. So let's look at chloride. Well, chloride is generally soluble. Let's take a look to see if silver is an exception. Silver is an exception. So therefore, we need to say that this is insoluble. So this is how one could apply the solubility rules. And this is a very general way of applying these solubility rules. And it's important to practice with these so that you become familiar with them. Now we need to look at this in terms of kind of a more practical way of doing this, where we're trying to determine chemical reactions that are occurring. So if we look at an example here, let's say we take silver 1 nitrate, AgNO3, which is aqueous, because all nitrates are soluble. So this will dissolve in water, so therefore it's aqueous. And we add to it KCl, aqueous. And all 1A metal compounds are soluble in water. So again, AgNO3 is soluble because all nitrates are soluble. KCl is soluble because all 1A metal compounds are soluble. Chloride also has a rule, which is soluble. So these two things will mix. So what's going to happen is you're going to end up with Ag plus and NO3 minus in solution. Here you're going to end up with K plus and Cl minus in solution. These are going to both dissociate because they're both soluble in water. Now, if Ag continues to interact with NO3, that's not chemistry. So Ag's choices are to either interact with Cl minus or K plus. What is Ag going to choose? Well, Ag is positively charged, so this is Ag plus. So Ag plus could potentially interact with Cl minus. So this could potentially interact with this. And K could potentially interact with NO3. Now let's look at the solubility rules. Before we continue this reaction, we need to see if something that's not soluble will form. Is AgCl solid or is KNO3 solid? Well, if we look at this, KNO3 is definitely not going to be soluble because it's got potassium in it. Potassium can't form in an insoluble compound. So when potassium interacts with any other ions, they're going to be aqueous. We need to form something that's not aqueous, otherwise we just have ions floating around in solution. So let's look at AgCl. Well, if we look at our solubility rules, and we already did this one, we look at Cl minus, which has a rule, and it's generally soluble. However, silver is an exception. So when AgCl forms an ionic compound, it's going to precipitate. That is the driving force of this reaction. This reaction will occur if you form something that's not soluble, or something in this case that's solid. So if we look here, we have form AgCl, which is solid, plus K plus and NO3 minus, which is K plus NO3 minus. We cross the charges like so, and we end up with KNO3, which is aqueous. And I should have shown you that for AgCl. It's Ag plus, Cl minus, cross the charges, and we get AgCl. KNO3 again is soluble because potassium and nitrates are always soluble. Now we need to balance. Well, we have one silver, balance polyatomic ions as whole things, one nitrate, one potassium, one chloride. So this is what is known as the molecular equation. This is the molecular equation between silver nitrate and potassium chloride, and it is balanced. Now, we can think about this in terms of the ions that are reacting. So anything that's aqueous, we need to break into its ions. Well, AgNO3 will break up into Ag plus, aqueous, plus Cl minus, aqueous. KCl will break up into K plus, aqueous, plus Cl minus, aqueous. And again, these break up because the solubility rules tell us that these are soluble compounds. And this will form AgCl solid. This does not break up into its ions because this is not soluble in water. So we end up with AgCl solid. This one does break up, plus K plus aqueous plus NO3 minus aqueous. And what this is called the total ionic equation. So in the total ionic equation, we break up all of the ions that are aqueous into their component ions. And if you'll notice here, when we started the reaction, we had K plus floating around in solution. And, this should be, I made a mistake here. This should be NO3 minus. And we had NO3 minus floating around in solution. If we finish the reaction, we still have K plus floating around in solution, and we still have NO3 minus floating around in solution. Said another way, nothing happened to K plus and NO3 minus. They're just floating around in solution. And therefore, if for the total ionic equation, any ions that are on both sides can cancel out, and we call them spectator ions. In this case, those are K plus and NO3 minus, because they have broken up and they're just floating around in solution. Nothing happened. They didn't precipitate. They're basically the same thing. Now if we write what's left, Ag plus aqueous plus Cl minus aqueous yields AgCl solid. This is what's called the net ionic equation, which is the aqueous ions forming something that is not aqueous. So in the molecular equation, we have everything. In the total ionic equation, we break everything that's aqueous into its ions. Then for the net ionic equation, we cancel out ions that are on both sides, which gives us the net ionic equation. The spectator ions are ions that are aqueous on both sides, the ones we canceled out. So that's basically how this works. Now, let's look at this if we wanted to go directly from the molecular equation to the net ionic equation. Well, if you wanted to go directly, first of all, you need to look at what did you form that's solid. So start with writing your solid product, in this case AgCl, solid. So this is what we formed. Well, what do I need to form this? I need Ag plus aqueous plus Cl minus aqueous. And we can go directly from here to here without having to go through this step and cancel out. I do need to show you this, but there is a direct way to get here. Also, if you were asked for the spectator ions, look for ions that are aqueous on both sides. Everything is aqueous on the reactant side of here, so we don't need to consider the reactant side. What are the aqueous products? Well, they are K plus and NO3 minus, which are your spectator ions. So you can do it directly that way. Let's do another example of this. Let's look at calcium nitrate, CaNO3, 2, aqueous. Nitrate salts are always soluble, so this is aqueous, plus sodium phosphate, which is Na3PO4, aqueous. Again, sodium salts are always soluble. So here we have two things. Well, calcium in a double displacement reaction is going to interact with phosphate potentially, and sodium is going to interact with nitrate potentially. We need to see if something that's not soluble forms. Well, if we look at our solubility rules, here is something insoluble going to form. And what we find is there's no rule for calcium, so let's check the rule for phosphate. Phosphates is generally insoluble. Is calcium an exception? It is not. So calcium and phosphate will form something that's insoluble. So this reaction is going to go. Sodium and nitrate will not form something that's insoluble because 1A metals and nitrates are never insoluble. So we don't need to worry about that. So what's going to form? Well, in ionic compounds, it's calcium 2 plus and PO4 3 minus. Cross the charges. And you end up with Ca3 PO4 2. So Ca3 PO4 2, which is a solid. The other one is Na plus and NO3 minus. So we have Na plus and O3 minus. Cross them. And you end up with NaNO3. And NaNO3 is aqueous because 1A metals are always soluble and nitrates are always soluble. So here is our equation. Now we need to balance it. Well, if we need 3 calciums, we're going to need 3 calcium nitrates. If we have 3 calcium nitrates, that gives us a total of 3 times 2, or 6 nitrates. Notice again, I'm balancing the entire polyatomic ion. If I try to balance oxygens, I'm going to give myself a headache. So there are 3 times 2 nitrates, so that means I need 6 nitrates over here. Well, in order to get 6 nitrates, I need 6 sodiums. Well, there's 3 in each, so I need 2 of these. That gives me 2 phosphates and 2 phosphates, and now I have a balanced chemical equation. So first, I found the products. I made sure that one of them was insoluble before I found them, and then I balanced the chemical equation. Now here, I want to go directly to, I'm not going to go to the net ionic equation, although I will do that in a minute. I want to go directly to the net ionic equation. And in a minute, I'll do the total ionic equation. But here's the net ionic equation. So in the net ionic equation, I need to form the solid product. So the solid product here is Ca3PO4 2 solid. Well, what ions do I need to form this? Well, I need Ca2 plus aqueous plus PO4 3 minus aqueous. And I can either use these stoichiometric coefficients or I can just balance it. I need 3 calciums and I need 2 phosphates. And you'll see 3 calciums, 2 phosphates. So this is my net ionic equation. I can also identify, without having to do any extra work, the spectator ions. And those are the ions that are aqueous on both sides. Notice that everything is aqueous on the reactant side. So I need to look at the aqueous products. Well, the aqueous products are Na plus and NO3 minus. These are just floating around in solution. If you needed it, you could develop the total ionic equation. And the total ionic equation involves finding the, it involves breaking these into their ions. So you need to keep the stoichiometric coefficients. So in this case, I have 3 Ca2 plus aqueous plus 3 times 2, 6 NO3 minus aqueous plus 2 times 3, 6 Na plus aqueous. So I'm just breaking everything that's aqueous into its ions, plus 2 times phosphate, 2 PO4 3 minus aqueous, yields. Now, if it's solid, you don't break it up. Ca3 PO4 2 solid plus, this is aqueous, so I could break it up, 6 Na plus aqueous plus 6 NO3 minus aqueous. So now I have the total ionic equation. If you notice, there's 6 nitrates on this side and 6 nitrates on this side, 6 sodiums on this side and 6 sodiums on this side, and the things I canceled out are the spectator ions. If I write what's left, what's not canceled out, I end up with this net ionic equation. So this is Molecular equations, this up here is the molecular equation, the total ionic equation, and the net ionic equation. It also shows us how to identify those spectator ions, which are the ions that are aqueous on both sides, which are identified by finding the aqueous products. Let's look at another example. In this case, let's look at NaNO3 aqueous, which is aqueous because both sodium and nitrates are always soluble, plus KCl aqueous. And we want to find the product of this reaction. Well, in a double displacement reaction, the Na is potentially going to go with the Cl, and the K is potentially going to go with the NO3. Now, if you form NaCl, it's going to contain a 1A metal. It's going to be aqueous. If you form KNO3, it's going to contain a 1A metal, and it's going to be aqueous. That means you're going to have a bunch of ions floating around in solution. In both cases, both the products and the potential reactants, it's just ions floating around in solution. This is not a reaction. This is a mixture, like Gatorade. Gatorade will have some potassium salts and some sodium salts in it, although probably not sodium nitrate, probably sodium chloride. Okay, so these are just ions floating around in solution. If you don't form something that's not aqueous, it's just a mixture. It's not a chemical reaction. So in this case, it's no reaction. So it's very important, like in the previous two examples, that you form something that in this case is a solid, and these are precipitation reactions, that you form something that is a solid, something that's not aqueous. Otherwise, no reaction is occurring.